There are 8 million YouTube talks online, but if you want to really experience it, you have to come in person. It's great. I mean, you'll just meet such cool people.
Good afternoon, everyone. Thank you for joining me. This is called C++20 Loves SQL. And I think this is a good test for, does your code work with Unicode, right? I think most of the other presentation titles are just ASCII, and I was like, hey, can we try Unicode? And I actually put in hearts there, and John was like, hey, we actually work with Unicode, so I put in a heart. So anyway, so we have C++20 loves SQL. Some of this stuff is going to go over some of the stuff I talked about yesterday. Was anybody here at the presentation yesterday for Metastruct? Okay, I'll review some of the things that some of the important points, the high points of that, just briefly as a background when we get into the implementation of this. All right, so this talk, the overview of the talk, I'm going to talk about SQL. I'm going to look at C++ example, and then I'll talk about the implementations of how we did this library, some of the techniques that we did. All right, so SQL is probably the highest level mainstream programming language. In terms of abstraction, right? It basically, it's very declarative. You tell it what you want. And if you tell it what you want, it will figure out how to do it. There's all sorts of query optimizers for all those things. It'll figure out what tables it needs, what indexes it needs, whether it needs to do a whole table scan or can use indexes. It's got all sorts of heuristics. In terms of the ones that most people that are mainstream and widely used, SQL is probably highest level language. And it's been around for a while, and it will probably likely be around for a while, right? Because it matches the capabilities of a relational database. The databases have proven to be very resilient and a very good mapping for the problems of data storage that most organizations have. And they're very widely used. So SQL is very widely used. And if you have some sort of SQL problem, right, you'll be able to find somebody that knows it, right? Like, how do I do this query? How can I do this thing? Even some real crazy complicated stuff, it'll be on Stack Overflow, it'll be on the internet, on a blog. Like, if you have a problem, probably somebody has already come up with a solution for the query somewhere. All right. So for example, we're just going to do a simple database just for example. We're going to have customers and we're going to have orders, right? And this is the strawman database, right? So our customers, we have an ID and a name. And our orders, we have an ID, an item, the customer ID, which links back to which customer ordered it, and the price of it. All right. So this is the SQL that we would use to create the customers table, right? So we just call create customer table, ID, integer, not null. We tell it it's a primary key, and we say text is not null, and it'll create for us. And not null means that we need to provide a value in there, and primary key tells us, hey, this is the main index for this, and if you insert it without the primary key, it'll automatically create one for you. Similar thing, we create the orders. Again, we have the various data types, text, integer primary key. And then we can insert a customer. So we can say insert into customer's name, and we say values John. So inserts a value for us. And then we can say, hey, let's say I ordered a hoodie at CppCon, right? So it's, hey, I ordered a hoodie for $10, and I've got one, I'm customer ID 1, and I have a hoodie. And then I can say, hey, I want to query, hey, give me all the orders where the price was greater than 5. So it'll come back and say, hey, John ordered a hoodie with discount code CppCon for $10. Okay, but now it's like, hey, I don't want to always pick 5 all the time. So instead, I'm going to take this SQL string, and C++ doesn't have interpolation, but pretend we did, and we interpolate in price from user. Does anybody see any problems with this? All right, shout it out. Anybody remember this one? Bobby tables. If people talk about this, if you say Bobby tables, and I think, what is it? Randall Monroe also has this. There's about 10,000 people a day that are learning it for the first time. So if you're one of the 10 seen Bobby tables, I hope you enjoy it, right? So basically, SQL injection attacks is if you allow like the user to put in strings and you just paste strings into your SQL query, they can do all sorts of wonderful stuff like drop off tables, delete your database, insert, manipulate your database, do all sorts of very interesting things to you. And the way to get around this is not to write some sanitizer for your SQL, like, oh, is this a good string or a bad string? Because as soon as you come up with a sanitizer, there's somebody that will come up with something that'll try to escape your sanitizer. So that way, doing that way lies, is a Sisyphean task. It will cause you pain and agony and late nights. Instead, what you want to do is you want to have the database help you out, and they have these things called parameterized queries and prepared statements. So what you do, you say, hey, this is a question mark. You put a question mark. There's various other syntaxes for this. And you say, hey, this is my query, and I'll provide you the data that goes in it later. So then this actually can increase performance, because you're usually not querying just once. So the database will pre-compile it, figure out how it's going to do, and then you say, hey, can you substitute in this value there? And no matter what they put in there, the database knows it's not the SQL query itself, it's just data. And so it will take the responsibility of keeping you safe. So we want to use parameterized queries wherever we can. All right. So in terms of C++ and doing it, how can we interface with SQL, right? So now we're kind of in the C++ mode. So there's three main ways going up in abstraction away from SQL. There's traditional database libraries that just use strings. There's the domain-specific language, and you can do object relational mapping. All right, traditional library with strings. So this is what most people think about first when they think of a database library, right? And these are the ones like, hey, MySQL or PGSQL or the Oracle database library. They basically, a lot of times, they represent the SQL as strings. They do have support for doing parameterized queries. They have first-class support. Many of these are written officially by the database team itself. It's supported by them. They allow you to access the full power of the database. And again, there's lots of information available for how to do stuff since we're using full SQL, right? You can go query, you can copy and paste what you have, and there's a lot of information available. Like you won't get stuck like, oh, how do I do this query? Because you can figure it out. However, because they use strings, even though they have the prepared statements, people can still be tempted, hey, why don't I can just create a string at runtime and pass it in there. So they're vulnerable to that. The other thing is because they're strings in the database, they're using strings, they don't know the exact types that they're expecting and are coming out. So you can have parameter mismatches like, hey, it requires one parameter, you didn't supply it. That can be a problem. And also when you get your row back, you had to kind of like, dynamic type, it's like some type of variant or some type of dynamic type where you had to figure out, okay, is this, is this, you had to create it, is this a string? Is this a integer? You had to do some casting there, casting or type conversions. Going up a little bit different, is domain-specific languages. So in that one, we use types to encode SQL, right? Like, so we basically allow us, instead of using strings, allow us to write SQL using, C++ statements. And it looks more like regular C++. So instead of select and like where, we can actually have comparison operators in there via overloading. We can It looks like regular C++ code, and it also provides great type safety because it typically requires that you put in the database schema. So you have some way that you tell it what the database schema is, and it'll create all the types for the tables and columns and the rows and all that. And then you can program pretty similar to normal C++. A great example of this is SQL PP11. It was presented here, I think, several years ago at CppCon. Then going further out still, you have the object relational model. And that one, the database is more of an implementation, and the more focus is on the objects and the graph of objects. Like, how do I efficiently store and retrieve objects persistently? And a lot of times, these generate the SQL themselves. So, and they're very, very convenient if you're on the happy path. Like, if you're doing something that they anticipated, that they support, I mean, everything will work out good. I mean, you'll be able to crank stuff out and like, hey, I don't even need to think about SQL. I don't need to think about the database. This just manages it. However, if you get off the happy path or you need to do something a little bit different that they haven't thought about, then it can be a pain to figure out, hey, how do I do this? In addition, there's a much smaller world than the SQL world, so there's fewer people maybe answering questions. The other thing is there can be performance implications in that you may not generate the most efficient SQL depending on what you're doing. All right. So for this one, in terms of like what I wanted to try to implement, we want to kind of keep with the SQL but do compiled time strings. So basically, we have the advantage of using almost raw SQL. So we can still, convey back and forth. But we still want to have typed rows and parameters. And because it happens at compile time, we can do SQL injection because it's a compile time string. And the other thing in terms of when I was making it is, I tried making like a DSL for it, but like, SQL is pretty complicated in terms of all its power, right? I mean, there's like tons of joins, there's subset queries, there's all sorts of stuff. I was like writing like, oh, I'm almost done. It's like, then I read some specs like, oh no, I'm not. So I was like, all right, this way is like, I don't want to write a whole SQL engine, so let's just see something simpler. The other thing with this is it supports more interactive development. So sometimes, like when I first started out, I was like, okay, let's write this library. A lot of times you think, oh, I'm going to generate my SQL queries, programming from first principles. And I'm going to go up there and I'm going to look at the types. I'm going to see what I need and do with it, and just write out the code. In actuality, at least for me, a lot of my SQL queries actually came from like opening the SQL database, querying stuff, finding what worked and what didn't work, and then copying and pasting and putting it in, and then maybe, turning it into a program. So it was more interactive. Like I wanted to be able to go back and forth from your program to like the terminal for SQL and like, move things back and forth so you can experiment and play around with stuff. And the other thing is I didn't want to provide schema because, this customer database, oh, that's really simple. But in the real world, like I think this is music brain schema, like, database schema is complicated. How many of you at your work have seen like a printout of your database schema anywhere? Big, small, complicated? Okay. Yeah. For us, the previous company I worked before Google, like we had like a giant wall poster with the schema on it. So it's like, okay, you look up there and you find the table, and that's probably fairly typical with like real world use database schemas. And in contrast, usually the queries themselves are a lot less complicated than the whole database schema. All right. So any questions so far before I start going into the library? Okay. So now we're going to switch there. I guess because we use Metastruct, I just called it Metastruct SQLite. I used SQLite just because it's easy. It's really easy to deploy. It's an embedded database. It kind of like does the principles very well. Easy to test. And we could extend it to support others. There's no macros and there's no code generators. So let's see how we create the customers. So we just have an SQLite 3 database. It's a really thin wrapper. And we do an SQLite 3 open. And then we do this prepared statement, and we pass in the query as a template parameter to it. And then we construct an object, the prepared statement object called SQLDB, and we call execute on it. So this just constructs a temporary object and runs execute on it. All right? So creating orders, same thing. We just put a string inside the template and passing SQLDB and call execute. So nothing real complicated going on. The only thing is the string has to be available at compile time. So there's no way that we can actually take data from the user and accidentally, or even if we were being, or even on purpose, try to introduce an SQL injection attack, because it has to be fixed at compile time. All right, let's insert a customer. So we use prepared statements. So insert into customer name and values and the question mark. And then pay attention to what is highlighted. We'll come back and look at that later. So, like a C-style comment, :name, :text. And then we have, look up a customer by name, right? We can say prepared statement, select, and we say :integer, a name equals question mark, :name, :text, execute single row, and we do braces, and we pass in arg name equals John. So John will get substituted in that question mark. And again, we're kind of like the principle of the pit of success, is that whenever you're designing things, you want to kind of like have your users fall into the good thing to do, the happy path. They fall into the pit of success. It's not like the bad thing to do is easy and the good thing to do is hard, right? Like gets, like in C, like gets is the easiest way to get something from get an input from the terminal, right? Or from the console. But it turns out to be the bad thing to do. We want to do the opposite and like make the good thing the easy thing to do. Okay. Back, okay. Sorry? Or okay, so what it is we're executing a single row. It's giving us, for that one, it's giving us back an optional. Because it may not be a single row. If it's empty, then it'll just, it just gives us an optional. So yeah, customer ID, we just, get ID, we check if it's there or not, and then we can call get ID on the ID or value. And then we have a prepared statement, same thing. So then in this one, we actually create a separate object called insert orders. And then once we have the prepared statement, we can call execute on it. So we can say execute with different parameters each time. So, when we have a phone, when we have a laptop, when we have a MacBook. In our thing, we see the question mark for the discount code. We see text question mark. And that basically means, hey, this is optional. So we can leave out the discount code. But the other items, they don't have the question mark by them. So if we leave them out, we will actually get a compile time error saying, hey, we have not provided, hey, you didn't, your thing, you didn't provide it for me. So you will get an error at compile time. And then we can do a query orders, right? So same thing, prepared statement, raw string. We tell it what the types of our columns are. Integer, text, real, discount code, and question mark, that's optional. And then, we have a min price. And we create an object. And then we can say execute rows, right? Argmin equals min price, and it gives us, we can do like range 4, and we get a row, and then we can read the columns that we have from it. And if we get the names wrong, again, we'll get a compile time error, not a runtime error. And the types are what you specified. So for the discount code, it gives you an optional double. For the item, it gives you a string view. For the order ID, it'll give you a order ID. It'll give you an integer, and sorry, discount code will give you an optional string view. All right. So when I was coming up with this, the key insight was for when you're dealing with the SQL and typing, you don't really care what goes on in the middle, like all the subsets, all the subselects, all the joins. Like those are kind of opaque to you. Those don't really matter to you once you're done with them. What matters in terms of typing is your columns that you selected and your parameters. And then so you just annotate the select columns and the parameters. And because you're annotating right in the query, like it's right there where you do it. Like as you see them, you do it. And the SQL has C-style comments, as I mentioned before. And so these are actually valid SQL statements. You can cut and paste them back and forth into your terminal, see if they work, see if your database actually works, you have permissions, all that. So we can go bidirectionally. In the annotations, what I did for the columns is, comment, type. And we don't have to put the name because the column name is just immediately to the left of that comment. Select whatever column you have and then type. And then for parameters, we specify the name for them because there's no name in there for the question mark. So we do a name type. And the type annotations, text will correspond to a string view, integer will correspond to an int64, real will correspond to a double. And for any of these, you can put a question mark at the end and that'll turn it into an optional of whatever it was. So if you put a text question mark, we have a question here, go ahead. For this one, I just did the very primitive types. I was mainly using SQL. The question is, SQL has a lot of types, very rich. Did you implement all of those or just these ones? For this one, I implemented these ones, mainly because I was using SQLite, which actually doesn't have that many types. I think the only one I don't have is really blob. And the other thing is, I will show you as we go through the implementation, like adding another type is fairly easy to do. Was there a question online or? Okay. All right, yeah, very good question. All right. So for the implementation, I'm going to go over a couple of things. We'll go over fixed string, metastruct, and required, and then we'll look at how we turn the string into a type specification that we can turn into types, and then how we bind parameters and read rows. So all right. So the main thing that came with C++20 is it allows us to pass in class types as non-type template parameters. So up until C++20, you could not pass in a string, like a string literal, as a template parameter. With C++20, you can now pass in non-type template parameters that are classes. You just had to do some magic to them. And what you need to do is, this is an example of fixed string. It's basically in the paper, it was in the paper for that feature. The original had a type template on the char type. For this one, I'm just using char, so I just got rid of it. Basically, you need, this is the magic. Sorry, this is the magic thing, the spaceship operator that's defaulted. And with the spaceship operator defaulted, that's part one. And the other thing, it needs to be like what's called a structural type. It can't have any references and it can't have any pointers. With the operator defaulted, the compiler knows how to compare two types or two values and know they're the same value. So then because it can compare them, then you're allowed to use them as a template parameter. And then the bottom of it is what is a class template type deduction guide. And what that allows us to do is we won't have to specify the n when we use it. We just say, hey, if you see us calling fixed string and we're passing a array, a constant char array reference of size n, make a fixed string of n minus 1. All right. So last time I talked about metastruct. And what this kind of uses it to create like a struct-like type or similar to it that you can actually do different stuff with. Like you can have a reflection and do various things with. And so how you define it, you go member ID is an int, and member name is a string. So you're basically creating like two fields, ID and name. And then we can construct it. We can construct it. We can read the values of the fields. Here, we can set the values of the fields. And this is just a brief overview of the talk I did yesterday. There's a couple of slides from it. We can also construct it. We can, basically pass in like these named arguments to it, ID name, and down here the order doesn't matter. You can reverse them. And then we can make a member required, like you can't construct it without providing an ID or a name. Score doesn't have required, so it'll get a default value. So down here we pass in ID and name, but we don't pass in score. So score gets a value of 0, that's the default value, and ID and name you'll get a compiler error if you forget to pass them in. All right. So once we've done that, what we want to do is we want to turn a query string that we get at compile time into metastructs. And it's a little bit tricky because we need to cross the boundary of being able to process stuff and be able to pass it as template parameters and types. And it's really easy to lose const expert because you can have a const expert function that if you take like a string view or something, even though you were passed in a string view before, you can't use that string view as const expert anymore. You can't like create a template based on the size of the string view. So you have to do a little bit other tricks to try to get around that. So the first thing that we're going to do is we're going to parse the type specs from the query string. So we have the whole query string, and the type specs are the ones that tell us, hey, what's the name of this type, what's the name of the field, what'll be the type, is it optional or not? All right, and we have this parse type spec that takes a query string, and what we do is we kind of had to pass through it twice. We convert the fixed string. There's a thing that converts it into a const expert string, and then we also we get the counts, and the counts are how many fields do we have and how many parameters. And I won't go over that just string processing stuff, so we won't go over it. It'll basically looks up, okay, we have this many fields, this many parameters, and then we create a thing called combined types specs, and then we fill in the fields and the values into there. And then we return what's called the combined type specs. And you see the 3 dots, we skipped a bunch of stuff. That's just string processing. So I'm going to skip it. There's not, it's just normal stuff.
Hello, excuse me. We have a question from several slides ago. Question is, Hanna Diskova, forgive me if I mispronounced that, I believe can do fixed string in C++17. If that's solved, can you port theoretically your library to C++17?
All right, so the fixed strings, the ones that were done for 17, I know like Hannah's done it and Louis Dion has done those kind of stuff. Those were basically relying on a GCC extension to UDLs. That actually didn't make the language. And this was proposed actually to make it for C++20, but then they actually came up with a way to generalize it not just to strings, but to to different types that, so we can pass in, not just strings, but like full user-defined types as long as they meet a certain criteria. In terms of porting it to C++17, there is a way to do that. What you can do is you can declare instead of passing it in, you can declare it as a const expert string view, and you can pass in a reference as a template parameter as long as it's like a static or a global type. So if you do that, it becomes a lot more of a pain. You can actually backport this to C++17. Though in terms of accessing it, then you had to do some tricks like, accessing it by hash. It's not nearly as ergonomic, and it's more of a pain to implement, but you can get something close to this with C++17 with some tricks. But great questions. All right, so what is combined type specs? So combined type specs basically holds two arrays of size, with the field size and the param size of two arrays of type spec. And we can't use because we want to actually pass these as template parameters. So we can't use std array. So type specs is just a kind of const expr specialized version of std array that's just specialized for type spec. Because std array doesn't have the spaceship operator that's defaulted. So because of that, we can't pass in an std array as a template parameter, which would have been nice. But so this is just a really, thin std. We just store some data and we provide access to it. Type spec itself, what we do is we store the name, type, and whether it's optional or not. And the reason, and we use something called query substring. And like I said, we need structural types, right? So we can't have pointers or references. So what we do is we have the whole query string that's unchanged. So what we do is we can just store the substrings as an offset and a count into the big query string itself. And so basically, going back, so these type specs is just storing offset and counts of the name and the types all together, and then we can, along with whether they're optional or not. And so this just gives it to us. And why not string view? The big reason we can't use string view, though string view would be nice, is because it's not a structural type. And so we can't pass it. It's basically got a pointer in there, so we can't pass it as a template parameter. Though we can actually get a concept for string view, do our manipulation inside a function, and then use that to calculate offsets and so on. But we can't actually directly pass it as a template parameter. All right. So then the next part for fields, for the fields type, we want to turn all these type specs into a meta struct. And what we do is we pass in the query fields, the array of type specs for the fields that we calculated previously. There's a parameter called required, which tells us whether we should make the members required or not. For the fields, we don't make them required because we're constructing them ourselves. We need to default construct and then fill them in. For the parameters, we make them true because we want to call errors if their users aren't providing the parameters that are needed. And then we do the make index sequence to send in an index sequence for like the length of the field. And then for the meta struct from type specs, so this is your standard index sequence, meta programming trick, where you have a type that basically takes a type name sequence. Then you do partial specialization with size ti and the std sequence. And then what you can do is then you can have you've got a parameter pack that you can unpack. And so we say, hey, member from, we call this, we use this other helper template, member from type spec, query string, and we pass in the type spec, the individual type spec, and whether it's required or not. And we just use that type. And then here's member from type spec. So 2 slides for this one. So it does 2 parts. We have the required thing. It says, okay, let me get a query string. We'll use that later. Let me get, so the name stir, we can construct it from string view, and we can take the whole query string and do a substir. So the type spec, the offset and count are exactly what we need to construct a string view substring. So we just construct a string view substring, and then fixed string, I added something called from string view that'll, you provided the size and it'll copy the data from a string view into there. So now we have the name of the string, the name as a fixed string, and then we have the type as a fixed string, same thing. And so we have the name of the type as fixed strings. then what we do is we look up we convert to your question, we convert the string back into a type. And the way we do that is we just have a string to type. And we say fixed string tag, whatever it is, and just specialization. So integer type equals int64, text, string view, real, double. So if we wanted to add it, we just add another specialization, for decimal, whatever our decimal type is, or, for blob, we can say like std vector or span or something like that. So then the rest of the go ahead, question. In terms of when the output. So we can specify that we want allowed to be null. When you do the selects, right? You can optional. Okay, but in your select, you know that you're joining them. You're getting them from the join, right? Like when you write the query. Okay, so yeah, I guess for joins, we could talk about like, hey, do we need it to be with this one? I think you would probably get a default value in there as opposed to optional none because of the way it is. It'd construct a default value, and then you just get a default value for those, whatever the default value for the type is. I don't think you would actually get a compile time error for that, or runtime error default value. But thanks for bringing it up. All right. Okay. So then we convert it like with the conditional. We say, hey, is this optional or not? And we say if it's optional, we say it's we make it an optional type, and then we're done. We just say, hey, type is our member value type. And whether it's optional, if it's optional, if it's required, so it's a parameter, and it is not optional, then we return the FTSD required as our init. Otherwise, we get a default value. So if you don't specify required on there, you'll get a optional value. You'll get a default value for that. Any questions about these last two slides? All right, so let's go on to binding them. So bind parameters, so we just take the parameters meta struct, and parameters, they start with index 1, so don't start at 0. And there's a function called meta for each, which just gives us the members and says, hey, these are all the members in the meta struct. And for that one, we just call bind impl with the value of that. And bind impl is just an overloaded thing, based on what the value type is. If it's an int or a double or a string, it'll, read that from the SQL table doing, from the SQL statement object doing all the, all your casting and everything like that. We just check our SQL return and index. And so simple thing, this binds all our parameters. Then to read the rows start at 0, so we default construct the rows. And as the question was, if we can't read it, if it's null, we'll just get a default value in there. And then, we do a little bit of check-in to say, hey, did we get the expected rows in the, in our query output that we were expecting? And then for rows, the index is 0. And then we just say read row into, again, another overloaded function that just tapes a type and just reads that type, doing some casting and stuff from the SQL. So, so C++ 20 loves SQL, so we have, so over several slides, and also this code is around maybe 500 lines of code, total, and that includes, the SQL. It doesn't include the metastruct stuff, which is another maybe 250 lines of code. So under 1,000 lines of code, we've actually, developed something that provides, some safety, some convenience, and actually a very thin wrapper on top of SQLite. And it provides some extension points that we can do if we want to add more types or support other databases. Thank you so much. Questions? Go ahead. I could have, but for this one, I was
Sorry,
the question.
Can you repeat the question?
Yes. So the question is, could you have used a variant, and could you have used a variant, and then just have that read from the rows? We could have. My point was to try to get away from dynamic typing. Let me just go back here. Querying the orders. My point was to try to, like, when we're writing the query, we usually know what we're expecting from it. Like, we're expecting orders ID, like we know it's going to be some type of integer, right? Like a lot of times we've run the query, we know what the type is. Like it's generally fixed. So if we have that information, it becomes a lot more convenient for us to use, because then we can just get it and use it directly without having to do like a std visit or has alternative. We don't have to do that all the time. We can just access stuff directly. But I guess we could overload, like if you wanted to provide, I don't know what this type is, make this like a variant. It would be pretty easy to add that, like, hey, if you can specify like for the annotation, like, hey, I don't know what this type is, make it a variant, then it could make it a variant. Online question?
The question is, I'm glad you found a use for your metastruct, and I'm wondering if it was here wholly unnecessary, because it seems one could also implement with a map like a JSON or YAML parser.
Okay, so the thing is with the metastruct, what it gives us the compile time, static types. So with the map type, like JSON parser or something, it's still dynamically typed. So for this one, right, if you do orders.id, you don't say you forget the .id in there. You just say orders, or you forget the dot, you just go orders ID, right? If you did like a dynamic type, you get a runtime error in the middle of your code. This one, you get a compile time error, you get stopped saying, hey, we don't have this field. Like we don't have this field, so you need to fix it. Also, again, there's not as much casting. You get ints directly, you get the strings directly, you get the optionals directly, so you can just, like the line with the get discount code, right? We don't have to do anything else. We can just call .value or because we know it's an optional. Another question? Yes. Correct. And also, what happens if the type that you put in your comment in the query string has no relation to the type of the actual column in the table? Okay, great question. So the question is, does the query string get passed unmodified to the SQL? And what happens if you lie to them, lie to me, and libraries, it doesn't match at all. For that one is, I believe for null, it keeps it'll keep the default value. If it doesn't match, it'll throw an exception. So it's basically like, if you provide the right thing, it doesn't attempt to like try to actually access the database and check what it is there or not. So it will actually throw a value for you. The one advantage of like not doing any checking is, SQLite, for example, I think they added some more new functions, or like some more queries for like getting the last row or the timestamp or stuff like that. We don't have to be aware of it. It'll pass through. Another question from online?
The question is, in your last talk, you described metastruct as a T-Rex. What's the overhead on using metastruct in this library?
Oh, Good question. So yeah, T-Rex is a thing. So the overhead probably, so I haven't done any like performance tuning, and I haven't looked at, how it, what the compile time bloat and everything is. But even for Metastruct, like there's no like recursive types in there. Sorry, recursive template use. We're just using mainly parameter packs and lightweight inheritance, right? So Metastruct is probably, there's a chance that it's probably lighter weight than your tuple implementation. So it's on the order of that, or maybe less than that in terms of how heavy it is. So for this one, in terms of for what we're getting, we're probably not that far off from tuple, and pulling in variant and doing all the mechanisms there. That would probably also be very heavy. So I would probably say this is probably comparable to like modern, C++ library of the kind. Other questions? Another one online.
How do you check at compile time if the column name exists? Like you still have the SQLite file, which you need to query at runtime to see if it has the columns, don't you?
Yeah, I don't like. This one just sets it up, and if you don't have the SQL database, if you don't have a connection, if you're going over the network and the file's deleted, you'll get a runtime error just like you would with using any other library. It doesn't check for that. Oh, another question there. Go ahead. Okay. Okay, I'll repeat the question. The question is, how do you deal with SQL in light of the fact that there's different variants of SQL, like Postgres will return after an insertion, some of the other ones won't. And the way, I guess with the the C++ way of let the user deal with it. It's passed through the SQL, and it gets interpreted there. With that one, I think I was planning on adding more support for for some statements. When you execute, you get back a statement. So I'll probably have to look at how to be able to annotate the SQL just to let it know, hey, this is the type I'm expecting to get back. Any other questions? All right, then. Thank you so much.